PowerPoint number 17, if you can just pull that up. Okay, so this is it. This is what a Wheatstone bridge looks like. You're going to see it look like this, but it can look differently. Once we get to other representations of it, I'll try to point it out so you see where the similarities are. But essentially, it's a very simple looking circuit in the sense that it's got one power source and a resistor. I didn't think bad. 10, low on battery. I was charging it the whole day. So hopefully it doesn't die out because I need it. You can see that there are four resistors that are arranged in kind of a diamond shape. And and there's what we call a galvanometer, or I'm just going to call this a voltmeter. Okay, so there's a voltmeter across, and it's acting as a bridge between point D and B. Okay, so here that's why it's got the term bridge in it. So this is the bridge. Oops, bridge, and it connects those points in between. Now you have to be able to imagine that this is a kind of it's mixed of a parallel and a series circuit. It doesn't really a category, it's in its own category. And you'll see calculating the current that goes through everything is actually going to be quite annoying. Annoying in the sense that there's a lot of steps involved, and it's easy to just make a mistake, but it's not, it's very straightforward. It's just a lot of steps. And the purpose of a Wheatstone bridge, the purpose of creating a resistance circuit like this, is to be able to identify or to quantify the resistance of an unknown resistor. Right, so if I were to go back to this drawing here, if you notice, this one is Rx. It's the only one that has a letter next to it. This one is R1, it's known, R3 is known, R2 is known, and Rx would be the unknown, and it's serving us to be able to identify what this unknown circuit is, okay? This is what you guys are going to be able to do upstairs in the lab. I won't get into the problem on how to find the unknown down here, because you really do need to have an experimental value across the bridge in order to be able to identify that. All right, so I'm looking at a circuit here. I just ignore what's on the right there. I'm going to get to that in a second. When you're looking at this, if R1, 2, 3, and 4 were all different values, all right, and you could ignore everything that's in between. So ignore this voltmeter in between it, all right? What kind of circuit is this? What is this circuit? Is this a complicated version of what kind of circuit? Is that? Parallel circuit, so you're right. I would have my voltage source, and it's the same as saying this, right? That's what I'm drawing, except I took out the middle, and it's just a parallel circuit with R1 and R2. This is R1, and this is R2, and R1 and R2 are arranged how? In series, exactly, and R3 and R4 are also in series. And then each branch is going to be connected in parallel. Okay, that's the basic of what this circuit is. All right. Now, um, if I were to give you values for this, do I have one with values? I do not. Yeah, let's go straight to that with values. I'll come back to this in a second. Let's go to this with values. All right. Now I want you to determine what the voltage drop across each resistor is. Okay. So this is very simple. Ignore the beginning, ignore the middle part, and determine the voltage drop. So the first thing we need to do is find the equivalent resistance to find the total current. So we're going to do that. So R left. So the resistance on the left side here is 80 plus 120, and that's equal to 200. R right is equal to 480 plus 160, which is 640. Is that it? And these two are in parallel. So you can say that 200 to the minus 1 plus 640 to the minus 1, not to the plus 1, but to the minus 1. All that to the minus 1 should give me the total equivalent resistance for this circuit, ignoring what's in the middle. Can someone just do that calculation for me, please? How much you get, Valerie? Sorry, can you say that again? 152. Let's go with 152. Everyone's in agreement with that? Okay, so 152 is our equivalent resistance. That means with our voltage, we can find the total current. Can someone find the answer for that? Should be like maybe 0.68, something like that. 0.65? Okay. So I have my total current, and that's my current leaving the battery here. What's my voltage at point A? Sorry? The voltage, not the current, but the voltage. How much? 100. I haven't had any resistors yet. So there's 100 volts up there. All right. What is the voltage at point B all the way down here? 0. Absolutely, 0 volts. Great. And so there's going to be 100, because it's going to be in parallel now. There's going to be 100 volts on the left, 100 volts on the right. All right. We can figure out what the current is going to the left, right? The current going to the left is going to be the total voltage of that. So it's going to be 100 volts is equal to the current on the left. Current on the left multiplied by the resistance on the left, which is 200. So the current on the left is going to be equal to 0.5. And the current on the right is going to be, well, 0.65 minus 0.5, which is 0.15. All right. Now I have my current going through each resistor. I can find the voltage across each resistor. Okay? So if I have a voltage going across each resistor, here it's, oops, 0.5 amps here. And to be able to find the voltage is 0.5 amps for the current multiplied by the resistance. So in this case, it's going to be how much? You can do that in your head, right? Yes, you can. 40. 0.5 times 80 is 40. All right, the same thing for the bottom one. You can find that is 60 volts, and that makes sense because 40 plus 60 is 100. We're going to do the same thing on the right. This time the current is 0.15 amps. And we can find the voltage in each. That one I can't do in my head. Yep. 72 and 24 ou 28. It should be. It should add up to 100. $75, 25. I'm tempted to agree. Oh, okay. So is this 0.16 maybe? Okay. So I'm going to go with 75 and 25. It doesn't really matter. All right. Okay. So now here's the part where, so everything we've done so far, we've known how to do. This is basic stuff. We guys got quizzed on this. There's nothing changed so far. Okay. Now, what I need you guys to understand is if there's 100 volts at the top and 0 volts at the bottom, how many volts is there at C? What do you think? 60. Absolutely, because 40 of them get used up by the first resistor, and there's 60 volts left. How many volts are left at point D? How much? 25, absolutely. Because 75 volts were used up by the first come on, by R3. Therefore, there's 25 out of that 100 that are going to be left. Now, if I were to use a voltmeter and attach each prong, right? So remember, a voltmeter measures potential difference, measures delta V. If I'm able to measure delta V of between point C and point D, what is my measurement going to read? How much? 35, absolutely. All right, so this V out now is not ignorable. We need this value. This V out is 35 volts. Any questions on that? Yeah, Elizabeth. V V out, it doesn't really matter what the out stands for. It's just what it's connected to. In this case, it's connected to C and D. So it's basically measuring the potential difference between C and D. Yeah. Okay. All right. So let's go back now. So I have my resistance here. All right. And I have a potential difference that can exist between these 2 points. These two, the left and right sides of my diamond-shaped circuit. I can find that voltage difference. Now, what you guys need to absolutely understand here is that V out, if I were to take this voltage measurement, V out, or whatever you want to call it, I don't care what you call it, it's a voltage, right? If you take a measurement and that measurement says 0, then you have this relationship, okay? And this is one of the most important parts of this subject here, okay? When the voltage in between those two in the diamond shape and where that V out is between point C and D or A and B, whatever you want to call it, if that voltage reads 0, then you have a circuit, and that circuit's called a balanced circuit, right? It's written right here. And then you could apply this relationship that R1 has to be, the ratio of R1 over R2 has to be equal to the ratio between R3 and R4. That's the only way that this voltage between here and here are going to be 0, right? So if I had a circuit where everything was 10 ohms, right? If everything was 10 ohms, then I would have a value for voltage at each dot, but it would be exactly the same, right? So for example, let's say there was 3 volts here and 3 volts here, well then the potential difference across V out is 0, right? The difference between 3 volts and 3 volts, there is no difference, 0. Okay, and that's what we call a balanced circuit, and we can apply that ratio. You can say that the voltage across the bridge is 0 volts. Okay? So now let's go back to this problem here. We found out what the voltage across the bridge was. That's what we did. We got 35 volts, and that's the right answer. But now we want to find out what would the value of R4 need to be if I want to create a balanced circuit. All right, so I'm Xing this R4. I'm going to replace it by something else, and I'm looking for a value for it such that the voltage across the bridge is going to be 0. So I have to apply my rule that R1 over R2 has to be equal to R3 over R4. And please, please, please don't let me trick you by saying that this is R1 and this one's R3 instead of R2, okay? It's really the ones that are in series. The ratio of the ones in series have to be equal to the ratio of the opposite ones. All right, don't get caught up on the numbers. So in this case, it's going to be 80 over 120 is equal to 480 over R4. This is a no. And then R4 is going to be equal to, can someone do that? How much? 60? No, not quite. 720. So if I have a 720 ohm resistor at R4, my voltage across my bridge is going to be 0 volts. Very good. Now what you're going to go upstairs, what you're going to do is you're going to do the opposite. You're not going to know what the value of that resistor R4 is. Okay, so you don't know, you have an unknown resistor, you're going to plug it into R4, you're going to measure V out experimentally using a voltmeter and mathematically try to calculate what the resistor is. Okay, that's what we're doing upstairs. So when we go upstairs, I want you guys to do that right at the start. Okay. This one is a little bit more complicated. Now we have a special circuit. It cannot be considered series and parallel if you did in the last problem. It has its own category. And the reason for that is if I was a current, I can go up around here. And at this point, I can go either left or I can go right. But then once I'm at my next intersection, I can kind of backtrack and go there or go down. And if I'm at this point, I can backtrack and go there or go down and then go back to the battery. And that's weird because I can't really I don't really know the direction of the current, which one's got a stronger potential and all that stuff. So we could solve this using the loop rules that we did, the Kirchhoff's loop rules. But there is another method called Thevenin's method. And that's what we're going to look at today. It's Thevenin's method. I'm going to erase all this, and we're going to go through all the steps. Big disclaimer here. The steps are long. The first thing I want you guys to do is to calculate the total equivalent resistance, ignoring that middle resistance. So just remove it and calculate REQ. That's step one. $180 ohms. Good. Step two would be to find a voltage drop. Find a voltage drop across each resistance, except the middle one. So similar to what we just did before, right? So far we're doing good. We just have to do what we know. Yep, Elizabeth? Absolutely. Yeah, you ignore the presence of that middle resistor. Yeah, you can use 24 volts divided by 180. You'll see we might not necessarily need to. There's a simple way of doing it, but you can absolutely do it that way. Zach? This is the Thevenin's method. Thevenin. Thevinen. Okay, so finding the voltage across, that's going to be quite simple because I know that my voltage at this point and at this point has to be 24 volts and 0 volts, right? There is no resistance before and after those points, so I know that all of my voltage gets dropped across my bridge, and therefore I can figure out what my current is on the left, what my current is on the right. My current on the left is going to be 24 divided by 450. And on the right, it's going to be 24 divided by 300. Can someone tell me some values? The right one? Can I have just a few more significant figures? That's it? Okay. And on the left? 0.05353, right? That's like that. Just for the sake, so that we all have the same numbers. Yep, I'm okay with that fraction. The perks of not being a math teacher is I never have to deal with fractions. You guys may think that they're unelegant to have it in a decimal number, but instruments measure things in numbers, not fractions. Okay, so knowing that I have the current on the left, so that's my current here, and my current here, I can figure out the voltage drop across each of my resistors, which is what I want. In fact, I don't even want my resistance, my voltage drop across each resistor. All I want, actually, is my voltage at point, I'm going to call this point A, I'm going to call this point B. I want to know what my voltage at point A and point B are, okay? So do what you need to do. That's going to be step 3. Find the voltage difference between Vx and Vy. In this case, it's VA and VB. So you can go and change this. Call this VA and call this VB. All right. I need to find what those two voltages are. Go ahead and do that. So I know that VA is going to be equal to whatever this resistance is, R2. So 200, or 300 rather, ohms multiplied by the current going through it, which is 0.05353 amps. I'm going to need a number for that. 8. VB is 8, you said? So 250 ohms multiplied by 0.08 amps. No, don't listen to you. Okay. Wait. Okay. See, if I go back to this problem here, the voltage at this point was equal to the voltage of this resistor. And the voltage at this point was equal to the voltage of this resistor. So I'm finding, in this case, I'm finding the voltage for this resistor, and I'm going to use that for point A. I'm going to find this voltage. I'm going to use that for point B. Okay? Sorry, my slide keeps jumping around. I'm not doing that on purpose. Elizabeth. 16 and 20? Yes, you're right. Okay? So I have a voltage difference between A and B of how many volts? What's my voltage difference between A and B? How much? 4. Yeah, absolutely. Okay? So in this case, I'm going to call VAB is equal to 4 volts. That was my step 3. We're only halfway through the steps. Yay. Word complicated stuff. Is everyone on the same page so far? All right. Now here's what you're going to do. You're going to replace the original battery with a straight wire. Okay? So going back, you're going to replace this battery with a straight wire, one line, bam. And the second thing you're going to do is you're going to replace that middle resistor with the voltage difference of AB that you just calculated. All right. So if I were to redraw the circuit, I'm going to redraw it over here. What it's going to look like is you have your resistor in a diamond shape like that. And in the middle, instead of having a resistor, you're going to have a voltage difference of 4 volts. Right? And at the top, instead of it being connected to the battery, you're connecting it with a straight wire. Yeah. Well, which one is higher, the left or on the right? The volt, this is, the right's higher, so the positive is going to end up on the right. Okay, and remember the longer stem on the battery is the positive, is the cathode on the battery. Okay? It doesn't really matter though, because it ends up being the same. Okay, so now my circuit looks like what I drew on the top right now. And that circuit and this circuit are the same. I just redrew the circuit in such a way that they look like this now, because it's a much simpler way of representing it. So, but just to prove you that they are in fact the same. You have the current coming out of the battery, right, going into this parallel branch. Then it has the option of, let's say I'm here and I have the option of going there, or I have the option of going there before I go back to the battery. And if I went that way, I have the same option. I have the option of going there and coming back, or going around and doing this resistor going back. So essentially now these two are in parallel and these two are in parallel, just like you see here, right? Those two are in parallel and those two are in parallel. As you notice here, my new battery is 4 volts. And I'm actually going to combine one of the steps for you guys because I find it more simple this way. I want you to also put a resistor all the way at the bottom there, equal to that resistor that you removed, that 100 ohm resistor. Okay, so the hard part is done now. That was the complicated part, is that transforming that old circuit into the new circuit, that was the hard part. Now that you have this new circuit, all you need to do is solve for current and voltage across that resistor, this 100 ohm resistor. So you just need to do that now. You can do that easily. You have a voltage source with a simple circuit. You can find out the I and the V for this voltage source, for this resistor. So in this case, there's going to be an equivalent resistance here equal to 100. Is that right? Yeah. And you're going to have a voltage source here, which is going to be 40 something, 43, 42. So my total REQ is going to be equal to 242. My voltage is equal to 4 volts. Therefore, my current can be calculated doing 4 divided by 242. That I can't do in my head. 0.016, something like that. 0.016? Okay. So because all these are going to be in series, right, my current here is going to be 0.017 amps. And I can find my voltage by just multiplying that current by the resistance, which is going to be 1.7 volts. And that's how you solve that. Simple, right? Yeah. It's not that bad. It's just a lot of stuff. All right. I'll give you guys a couple seconds to finish writing. Yeah. Very good question, because it was a long time ago. It was to find the voltage drop and the current passing through that resistor. That's that's what the question's asking, and that's a mathematical way of solving it. You can use it. You can find it using the loop rule. Setting up a matrix, there are 3 loops here that you have to start. The loop rule is 1, and this is another. Yeah. So, so here are the remainder of the steps. We've done these now, and we found out that the voltage here is equal to 1.7. All right. Here's what you guys are going to do. I want to see you working on the walls. I want you to solve this problem. These walls. There's an eraser on the table for you. There's an eraser on the table if you need it. When you're done, please work on the next one. There's 3 problems in total, right?
So offended there. What? Nice girl. Wait, thank you. There's a witness. They're accomplices. Why? Can't find it. Oh, okay. And
That's not the answer on the slide. But it could be that I wouldn't rely on that because I didn't make the slide. I think your VAB is correct. Yeah, move on to it.
Have you met me? Why give them an easy problem? Why give them an easy
Wait till next week, we'll have to give them that capacitor problem that you have created. It's like a bug in my device.
I was freaked out. I was literally 25% getting
So here, how did you get this? How did you get these two numbers? B is where? Ah, okay, so here you made a mistake on this one. Yeah, so you use the total resistance to find. Oh no, that's correct. The current is correct. Both of them recalculate this. Yeah, so the left would take this number multiplied by this. What did you get? That's the one. Okay, so that's good. What about here? La différence, c'est vraiment 3.4? 3.4, c'est ça? There's something not right. That number is not right. So we need 0.47, que c'est pas parce que c'est pas à cause des Je vois pas d'erreur. Non, mais c'est vraiment quand même assez différent. Point 3.4, point 4. For example, two, there was a resistor. So yeah, I think when you guys, this is the trick example, that is not.
Oh no! Oh no! So it's just two parallels? Yeah. Yes.
Then keep going. If you go here or here, then when it's here, you can land with
So follow the circuit along with that.
here. Here. Here, if you go down. Again.
It doesn't have anything in the middle, just
Here.
Essentially, you could, except your resistance values would be one on three, or two on.
Yes.
What?
Yeah, girl, you're not joking. I'm going
This is actually a weird, it's a weird looking regular circuit. Just try to figure out what kind of regular circuit.
She wanted to serenade me with the song.
If you need to,
Now, what we're doing.
Speed plus five plus five. Go! Did you know math? You have exam next Thursday. Yes. This is Cindy at all.
Mais là, le pli, il est pareil dans l'empli. Le voltage là-dedans. Oui, mais en plus, parce que le voltage n'est pas pareil. Oui, mais il descend ici. Parce que ça, c'est en suivi de l'exemple. Le voltage qui tombe ici. Pour contrôler le voltage ici, de trouver le voltage là, puis l'autre, c'est trouver le. Voilà, ça. C'est compliqué. Non, on peut pas le faire là-dedans. Mais si on trouve le voltage. Oui, c'est ça. Si on trouve le voltage, on trouve là-dedans, on a déjà le voltage. C'est ça. ça, t'es 37,5. Comme resistance. Fait que là, dans tes composables,
Next one. Oh man. Great. Well, great on your computer.
c'est approuvé, là, c'est que tu vois, est-ce que tu fais mal à ta Oui, quand ils ont pu mettre le mot, c'est quoi? Mais quand c'est flat, c'est juste parallèle. Ça veut dire que oui, mais le. Mais peut-être pas parce que
I was gonna say it was going backwards.
Exactly, and the spoon, oh, you projection. Creating a shadow.
Always.
Oui, c'est L2. Non, mais on peut jeter oui, parce que lui, il y a le courant. Ah, il peut
One and four are correct.
When S1
Yeah. Alex, yeah. This is before this is closed?
Yeah.
Say. You don't know the answer. Let's try to. One second. Yep. Yep. Okay, so this is the trick. This is probably the trick. Because there's a short supposed to
It is speaking loud enough with deaf in the ear. On the other side, girl. It's not the thing. Are you doing me? Am I? Honestly. Also, I'm not a teacher.
You guys figure it out?
Right. Brother.
So il faut pas la redessiner. La ligne dans le milieu. Ensuite, on ignore les chiffres. Si tu as un courant, ça fait ici. Là, tu as un choix à faire à point on va la redessiner. Tu as un choix à faire à point ça va être à 1 ou à 3. Ensuite, après avoir fait le choix, il y a la connexion directe. Donc, ils se rejoignent. They connect to each other. They come back. So I can connect them again. And then after that, I have another choice to do. I can go here, or I can go here. So if I'm at this point, I can go like this. Or if I'm at this point, I can go like this. Or if I'm at this point, I can go there. If I'm at this point, I can go there. So I still have all my options. So that means that I still have all options. With R4 and R2. Then I'm here now. So it's just a regular circuit with two parallel circuits, two parallel rings. That's the trick. What did you guys mention? As long as you're okay, we understood it.
No problem.
What kind of power source is that? So what? I was thinking of one of those, like industrial England, industrial revolution Englishmen. Like Jack the Ripper.
We're done here. I'm sorry, there's a giant man in the middle of something, so I'm a little confused.
No, no, I heard that that looks like what you're. What are you?
I've been
No. Really?
I have no idea what I have no idea what's my guess. The only like this is
So just out of curiosity, just going back here, L3, is that L3 greater than L2 or dimmer than L2? I don't know.
dimmer than.
The last one is the dimmest. Okay.
And then we found the brightness.
Brightness.
Because the range going through one.
Now the current. All got brighter?
The left one is brighter. Maybe.
You're right, the question only has to go. You guys want to take a break? Meet upstairs at 2:30. It's just leave it up.
Even with that.
It's cold out there? It's really warm.
No, mother just thinks she's down. Valerie, you are representing everybody who travels by airplane. Oh, yes, you put it right now. Oh, I'm getting caught, no. French people, they pray for you. This is not that. You can die.
He's very rude.
The people who are, I don't know, nature, and if you love it, you're like, oh, if you want to love it, that's what you do.
The ground is
That was
lava.
the mountains.
No, the floor is lava.
Oh my god.
I've been watching those videos of like this yellow but person like jumps on something and just like
That's my
I can imagine you and Sam just like walking through the picture of Sam like in his lunch shirt
I gotta grab one. Thanks for the tea.
Yeah.
If this book came out right,
Sam only starts to melt as guys.
Like the Titanic.
that's chocolate strawberry.
I
love
it.
Okay, nice call.
For my birthday 2 years ago, you would be my
I'm trying to see if I have any in my house.
Tomato.
We also have some lessons in my house because my mom like drove out over there.
Yeah, that's what that is like what?
I can't believe that.
Again,
That's how my sisters do
and then when you do that, you just want your current no, not even, it's not.
Teacher talk. Well, actually, I'm going to stop you guys here because I want to pick back up in the lab in, let's say, 8 minutes. 8:30, 2:34 up in the lab. Take a few minutes break. I'll meet you guys up there. Okay?
Tout le monde à Lille ne veulent pas être avec Verdun. Je suis là, si déjà entendu quelqu'un à Lille de côté à Verdun.
Nombre d'heures d'absence, 2,5 en algèbre. Mais j'étais là à chaque cours, fait que c'est pour peut-être bon.
Okay, let's go upstairs, guys. Or just take a break and then meet you.